Okay. Now I will present the other hardware system that is developed within the Human Brain Project, which is the digital many-core approach, or Spinnaker. And this talk will give an overview about Spinnaker and especially the new hardware features that will be integrated into the next generation of the system. And then in the second part, Christian Meyer will give some examples of neuromorphic applications and the capabilities of the new hardware. Some of you, or many of you, might know the Spinnaker system. The Spinnaker stands for Spiking Neural Network Architecture, which has been developed at the University of Manchester by Steve Ferber. And it's a communication memory-centric architecture targeted for the efficient real-time simulation of spiking neural networks. And it's processor-based, so it the chip contains a number of ARM cores. The first generation contained 18 ARM cores per chip. And as Karl-Heinz Meyer said this morning, the system has a broad user base. There are around 40 to 50 systems all over the world in use. And its key, let's say, advantage is flexibility. Since it's programmable, it's adaptable with respect to the network, the neuron model, plasticity models, and so on. Since to the fact that it's real time, it's well suited for any application that interacts with the real world, like, for example, robotics. And in this particular example, it's faster than any high-performance computing approach. And the current system, as it's scaled in the Human Brain Project, has an overall capacity of approximately 10 to the power of 9 neurons and 10 to the power of 12 synapses. And this chip of the first version has been implemented in 130 nanometer technology. So within the Human Brain Project, obviously, there is scope for improvement, and we follow here two approaches. First, we switch on a more modern process with advanced features. Here we have chosen the 22 nanometer fully depleted SOI technology by Global Foundries. And on top of the pure technology shrink, we add on new circuit techniques to actually enhance the energy efficiency and the throughput of the system. And the overall target is to enhance the capacity over the then later on scaled machine to brain size networks and allow this simulation in real time at least 10x better efficiency compared to the current system. Now some details about the hardware of Spinnaker 2 and the chip. So this is the overall Spinnaker 2 hardware roadmap as we plan to implement this within the Human Brain Project. And the overall idea is to scale the current version of the Spinnaker 1 system, which is located in Manchester here, which is capable to approximately simulate networks at a size of 1% of the human brain, towards a system that is capable to simulate brain size networks. And to achieve this, there's a roadmap of various silicon prototypes. There's one 28 nanometer prototype where I will show some measurement results later in the talk. And from this year on, we switch to 22 nanometer and finally plan to implement Spinnaker 2, which contains 144 ARM M4F cores with some advanced features, as I will show in the following slides. So this is a comic slide to show how the Spinnaker 2 chip will look like. So we have this chip, and when you look into this, this will be an active piece of silicon located under a package-on-package LPDDR4 memory, which is then, of course, used to store synaptic weights in the system. And the chip itself is a homogeneous many-core architecture, which contains these processing elements organized in quad structure. So we have 4 PEs, 4 processing elements connected to a quad PE. And here is a network on-chip router, which works as the communication fabric. And there are, of course, communication channels to both the memory and other chips. And the packet routing is done with a Spinnaker router, similar to the solution in the current system. There's a prototype of this quad PE to be taped out within the next month in 22 nanometer technology. And this is the latest layout picture of this basic element. So to show you some details, what are now the new features within this processing element that enable more energy efficient neuromorphic computation, I'd like to show you this brief block diagram and highlight some features. As main component, of course, the processing element is based on an ARM Cortex M4F, and this F is important since now this contains floating point support, which was not available in Spinnaker 1, but is of course an important type of function for various neuromorphic applications. And then on top of the ARM IP we use here, there are some features we add. The first thing is that I will highlight in one of the next slides is we add dynamic power management, which contains dynamic scaling of voltage and frequency, and of course power shutoff for unused cores to enhance the overall energy efficiency of the system. Then we allow memory sharing, synchronous memory sharing to processing elements that are located next to the active one. Synchronous memory sharing means that these cores, when they operate in a scenario where they have the same clock frequency, they can synchronously access the memory of the others. That allows us to have a very, say, homogeneous and scalable fabric of both memory and processing elements in the system. Then we have a multiscale accumulate accelerator, which can be used for machine learning, of course, and this is directly coupled to a DMA, which can then autonomously compute matrix multiplications and convolutions. And then we have some special neuromorphic function accelerators, like, for example, a solution for the exponential and log functions, and generators for random numbers, where both pseudo-random numbers and true random numbers from real PLL noise from the systems are supported. There's a network on chip for spike communication and a Spinnaker packet handling, and for the implementation, this core is enabled for adaptive body biasing that allows ultra-low voltage operation at the minimum energy point in 22 nanometer CMOS. Yes, and this is about the implementation strategy. The talk was entitled towards energy efficient system, and we asked ourselves the question what to do to make the Spinnaker chip more energy efficient. And there are, of course, two solutions again. The first one is to go to a process option that really supports energy efficient operation. We have chosen the Global Foundries 22 FDX technology. And for this technology, a spin-off of our group, RACEX, developed a adaptive body bias solution, which allows to adapt the body bias during operation for the baseline IP or foundation IP as standard cells in SRAM. And this enables operation down to 0.4 volt with worst case 0.36 volt worst case of these digital parts. And based on this IP, we did a lot of implementation studies to analyze the PPA, so it's the power performance area of the processor core, especially for the application scenario of these neuromorphic problems. And then we came up with plots like this, where we can measure the energy per operation for a certain task, and then determine for which implementation scenario of which nominal supply voltage to operate the core on, we get to this minimum energy point. When you go to lower voltages, you're limited by leakage current, and when you go to higher voltages, you're limited by the dynamic power consumption due to the high supply voltage. And now our system supports now two things. First, we can operate at this minimum energy point, which is at approximately 0.5 volt. And we can even support a low power mode, which is then not the most energy efficient one, but this ultra low power down to 0.45 volt here. But at the same time, we allow dynamic voltage frequency scaling. So the system can switch, as I will show in the next slide, to another performance level here called PL2, which is the operation mode at a higher voltage, as example 0.6 volt, and then at double the clock frequency. And this allows us to give this or reach the system performance when it's temporarily needed in the neural network simulation. And this is done like this. Each processing element has these header switches which allow it to connect to one out of these two supply rails. And this dynamic voltage frequency scaling has certain aspects. So it's fine-grained, so we can switch individually per processing element. It's fast. we can realize switching times below 100 nanoseconds, so it's nearly invisible from the software point of view. And it's, which very important, self-triggered. So each processing element, based on its local neuromorphic workload, can decide at which performance level to continue its operation. And this is done because the actual switching is, let's say, scheduled by the software that is locally running in the core, where based on neuromorphic workloads, like, for example, the number of incoming spikes within a certain amount of time during the simulation, is used as a decision metric at which performance level to execute the next cycle. This we analyzed in detail in a neuromorphic example, which is a SynFire chain, which is a network that shows a bursting-like behavior. And what you can see here is that the processing element switches to a higher performance level, PL, in case a high number of spikes arrives within a certain time frame. And if a small number of spikes arrived, it operates at the lowest level. And we can see that we can execute, in this example, nearly 90% of the simulation cycle at the lowest level in the minimum energy point, and only a few percent. In this example, we had 3 levels, but only in 2% of the cases we need actually to clock up to the upper level, which is then also the peak performance of the system. And with this metric, we can bring down the overall power consumption by 50%. Just to be adaptive, only to be adaptive to the actual workload that we see in the neuromorphic problem. Yes, and as last example for the hardware features on the system, this slide shows the integrated machine learning accelerator, which is a 16x4 multiply accumulate array that is equipped with a state machine that has direct memory access functionality. This means it can completely offload operations like matrix multiplication and convolution from the CPO, and it can even be operated remote controlled from other processors on the system, so the local processor can be completely shut off while this unit is running. And with this unit in this target technology, we expect to achieve on Spinnaker 2 at this minimum energy point, energy efficiencies of approximately 6.4 teraops per watt. So as interim conclusion hardware, I've shown you some approaches towards these realization of this Spinnaker 2 system as example for a digital many-cross system. And the techniques we used in here are motivated by a mix of approaches. So first, as I said, we are processor-based, as Spinnaker 1 already is, which provides flexibility. Second, we, let's say, offload some functionality that is often used in neuromorphic problems to fixed hardware accelerators, which gives us performance, and we enable very low voltage, in some scenarios even near threshold operation, which is enabled by 22 FDX and adaptive body biasing for maximum energy efficiency. And this system is able to perform like event-driven operations. This is, as an example, the dynamic voltage frequency scaling I have shown, and the realization of the communication, which is realized by energy proportional links for chip-to-chip communication. So now I hand over to Christian.
Okay, thanks, Sebastian. And just to make this more plastic for you, in essence, you know the old Spinnaker board, the Spinnaker 1 board, that's about a foot to a side, so it's a pretty hefty machine, 48 nodes, about 900 processors. We basically put this inside a single chip. You're getting a 10x scaling from all these features that Sebastian showed you. So that's brute force, then about a factor 2.5 from the clock frequency, and another factor 2 to 3 from the accelerator. So basically a 1 to 50 scaling in essence. Now what do we do with all this power? We have a range of benchmarks that we implemented on this first prototype we have in the lab right now. So the SynFire chain Sebastian has showed you, the rest is all testing different aspects of the system. And 2 of those, both with Wolfgang's group at Graz, I'm going to show in a bit more detail. So the one is reward-based synaptic sampling. Basically, so the characteristics, spiking, reward-based learning, and it's synaptic sampling of network configurations. So David, the guy in Wolfgang's lab that does that, calls it a scaffold. So he provides a general structure of the network, and the synaptic sampling is essentially rewiring the network to solve a given task, and that's ongoing rewiring. So the network is also very robust with respect to, for example, lesions, can recover from them. And yeah, benchmarks we got running at the moment is a maze task and task-dependent routing that's shown on the right-hand side. So basically based on a reward, information from the input neurons, those patterns P1 and P2 you see on the right-hand side, must get routed to these target areas T1 and T2. The whole thing is pretty much limited actually in a processor by the complexity of the synapses. So the synapse model is pretty involved. So we can do something like 3K synapses on a single core, and we basically need to optimize that a bit more. At the moment, this uses the random generator for this exploration, for the synaptic plasticity, uses the float, needs the float for the reward gradient, so you couldn't even do this in Spinnaker 1. Uses the exponential also for the synapse, and overall you get about a factor of 2 advantage, numerical advantage, that you wouldn't have if you didn't have the accelerator functions. And challenges here are, for example, the exp and the random, we put them in fixed point, and this problem needs them in floating point. So we waste a lot of numerical cycles putting this on the machine, just converting between the formats. So we're definitely across the next prototype still going to fine-tune those numerical aspects. Deep rewiring is about the same kind of stuff, just not for spiking. So that's for rate-based machine learning networks. It's actually quite interesting. So Wolfgang's group has put a paper out on that, and they compared it to state-of-the-art pruning. So that's structural plasticity, gets to up about 96% accuracy on MNIST for 1.3% connectivity. As you can see on the right lower side, it's a lot more, let's say, fail-soft if you go to extremely low connectivities. So your standard pruning algorithm, it fails essentially if you want to go below 5% connectivity, whereas for the structural plasticity, drops off gently. And on some problems, it outperforms pruning. And it was interesting for us in the hardware because from the beginning, you can have a very low memory footprint. Because I'm definitely agreeing with some of my predecessor speakers here, we want the learning on the chip. We don't just want an inference engine here. And with that, we can put the learning on the chip because we basically have the same memory footprint all through the algorithm. It's not like pruning where you basically need a large network and then you whittle it down for inference. You really have it all the way through learning. Same thing, uses pretty much all the accelerator functions we put in here, get a speed of factor, so a numerical advantage factor of about 1.5. Current efforts, we need to parallelize that. We need to go to low resolution weight. So at the moment, this uses single precision floating point. And we want to kind of couple the ML, the machine learning, with the event-based way of operation. So at the moment, this is standard machine learning, but we want to exploit the spatial and temporal sparseness that we get in the data. So really have kind of the machine learning also kind of event-based. And the last idea, which is actually then for the big machine, I want to go to multiscale modeling. Because, I mean, Spinnaker, of course, in the natural way of operation is pretty much point neurons or multi-compartment neurons spike-based. But for example, if you go to molecular dynamics, if I look at those equations, you need random generators. You need logs, app, maybe other functions. We need to look at that. So you basically can also, in these differential equations, encode molecules, ion channels. Then, of course, the spiking stuff. Then we can have rate-based neurons with the machine learning accelerator instead of the spiking neurons. And we can also basically use the machine learning as a black box where we encode a neural field model, for example. I've been talking about this with Chris Eliasmith, so expect to see something like that come out of Spinnaker 2 as well. And yeah. The motivation, essentially, apart from having all the numerics here, is that we basically need to go that way to have a full brain model on the final Spinnaker 2 machine, because we did the calculations, and even for the full-sized machine, we won't be supporting spiking neurons. but we can do it with rate-based neurons, and if we do a couple of approximations, maybe approximate, as I said, brain areas that don't interest us with some kind of mesoscopic model. So you basically need this kind of approach for a full brain model on Spinnaker. Conclusion? Yes, I like the technological singularity. Spinnaker 2 deployment approaches. So one thing is the small scale embedded for robotics. As I said, I wasn't kidding. We really want to put the 48 node board inside your single chip module, and that includes the periphery. So standard interfaces, USB, Ethernet, on-chip FPGA resources, so you basically can have an AR interface synthesized on there. So you really have a kind of brain on a chip for your robotic stuff, and that's operating at 1 watt. What was before an entire Spinnaker 1 board. Then, of course, the large-scale machine, so that's 10 million cores, and some pretty impressive figures. For the full machine, we get 5 petaflops in the CPU and 0.6 exaops for the machine learning accelerators. And the energy figures is spike-based, about 300 picojoules per synaptic update. If you go for the Mac units, it's 300 femtojoules. Applications, yes, multiscale modeling, because you have it all available in the ARM core, the Mac stuff, as well as the spike-based stuff, so you can do wild combinations there. Interesting problem is going to be the software stack. We're going to take over the Spinnaker style software stack for spiking, TensorFlow Caffe backend for the machine learning, but we don't know how to merge the two yet. And in Dresden, we're already developing a couple of derived concepts. So Dresden, if you don't know if you know it, it's kind of the home of the tactile internet, was coined in Dresden. So we're developing kind of smart sensor nodes for body area networks based on this whole Spinnaker 2 framework. Then automotive. I'm actually in a project with Volkswagen and Intel adapting this kind of stuff for automotive nodes and closed-loop neural implants. So kind of have this Spinnaker-style neuromorphic inside your brain. And yes, that's basically it. That's my group in Dresden supporting this and Steve's group in Manchester. Thanks for your attention.
It's very, very impressive. Is there any reason to think about 3D implementation rather than 2D?
So basically, we go with tried and proven industry in this case. So we really want to scale up the system, so the single node basically needs to be very reliable. This is one reason why we decided against 3D. We were looking actually at 3D memories, like the hybrid memory cube, compared to, for example, LPDDR4, but the hybrid memory cube has a lot of baseline power, so it doesn't scale with memory access. So we decided against the hybrid memory cube. And yeah, for the processors, it will be a basically system and package approach with the memory directly on the die. But as you need the memory and the die inside the package, it doesn't really make sense to stack more on top of each other. Because the interconnects, it's not going to get simpler in essence.
And can I ask one more question? For the, when you talk about the machine learning to be included, what do you mean?
Well, as Sebastian has been showing you, there is a full-blown multiplier accumulate unit with its own state machine. It basically gets told where in the memory are the activation functions from the last layer, where in the memory are the synaptic weights. Then it basically does the whole multiplier accumulate, and then it hands it back to the ARM core for the to applying the new activation functions. So you're offloading an entire layer of a machine learning network off the ARM core, and then you're handing it back.
Okay, so like a feed-forward neural network?
You can do...
Or you can do whatever.
You can do whatever, essentially, yeah. I mean, the single layer is, of course, feed-forward, but what happens after that is entirely up to the ARM core again. So the ARM core is kind of the supervisor of the machine learning.
Okay, thank you very much. Very nice work.